Hi, my name is Koi Katret. This is my channel, C Squared. I'm going to be doing mainly math problems on this channel, maybe some physics problems here and there. But yeah, so this is going to just be my first video, and we're just going to do some math problems for fun. So here I have problem B1 from the 1990 Putnam Exam. I'm kind of going to do an improvised session. I guess if you want to call it an improvised session. Shout out to like Flammable Maths, I guess. He does a lot of those. I haven't really tackled this problem yet, but it looks like it'll be pretty fun and it shouldn't take too long. The B1 problems, or like the first problems, tend to be easier than the rest of the exam. And this one looks pretty fun to do. Actually, I really like calculus, and like differential equations and stuff like that. I haven't gotten super deep into it. But yeah, let's just dive right in. So like I said, this looks a lot like a differential equation. We just haven't manipulated it in a certain way. So to undo that, I'm gonna take the derivative with respect to x on both sides. So I'm gonna have, okay, d dx, right? No. Yeah, I want to take it with respect to x. Yeah, okay. So then I'm gonna have d dx, and d dx. Okay, so the derivative of a constant is just 0, so that's nice, it's gonna go away. We are allowed to do this. I don't know the full justification for it, but I know we're allowed to do this by the fundamental theorem of calculus. So first of all, this derivative on the left-hand side is going to be 2f of x, f prime of x, okay? So that's just going to be the outer derivative times the inner derivative, and that's going to be equal to, okay, I'm going to write this in a certain way. I'm going to have the derivative of f of x. I'm going to call capital F the primitive of this thing, and then it's going to be subtracted from the primitive evaluated at 0. Okay, so the differential operator, which is basically just this, is a linear operator, so we can kind of distribute it into this f of x term and this f of 0 term. And since f of 0 is just going to be a constant, then this turns into 0. And like we said here, this is going to be 0. So I'm going to have overall d dx of f of x, capital F. So now we can take the derivative of this, which is going to be the derivative of the primitive is the integrand itself. And then we have to take, and we're evaluating it here, and we're taking the derivative, the inner derivative. So this is kind of going to be condensed a little bit. So we're going to have f of x whole thing squared plus f prime of x squared, and then the inner derivative, which is going to be the derivative of x. If this were like some function like x squared, if it were x squared, we would have times 2x, but it's not, so the derivative is just 1. And we're good. So now we can gather that 2f of x, f prime of x, is equal to f of x squared plus f prime of x squared. So this is just the difference of two squares. If you subtract 2f of x, f prime of x on both sides, so we're gonna get that 0 is equal to, let's just write f of x as y, and then f prime of x as y prime, just to lessen the amount of writing I have to do. So we're going to have f of x is equal to y squared minus 2y, y prime plus y prime squared. So this is a quadratic. It's the difference of a square. I think it's the difference of two squares. I always forget the name. No, it's not. Whatever. You don't need to know the name. You just need to know the form. It's gonna look like this. So we're gonna have y minus y prime squared is equal to 0. And now we can gather that 0 is equal to y minus y prime by taking the square root on both sides. And then we're gonna get that y prime is equal to y. Okay, y prime can be written as dy dx. Okay, and now I'm going to use separation of variables to do this. This is a pretty easy differential equation now if we just integrate it and find a constant, which is what we're going to need to do. I think the constant is going to have to do with 1990, because if we choose 0 up here, then we're going to get f of 0 squared is nothing but 1990. Okay, yeah, that'll work out. So then we're gonna get dy over y equals dx, and we're gonna integrate, and we're gonna get the integral of 1 over y with respect to y is the natural log of y. This is a really easy integral. And then x plus c, raising both sides to the e power to get rid of this natural log. We're gonna get y is equal to e to the x plus c, and by the exponent rules, we're going to get e to the x times e to the c, and we can rename this e to the c as a different constant. We'll just call it c again. It doesn't really matter. And we're going to bring it to the front, so we are going to get that y equals f of x equals c times e to the x. Okay, so now we have our function, and we need to find the constant now, and it's going to be pretty simple to do like what I set up here. We're going to plug in 0 for x, and we're going to get that f of 0 squared is going to be equal to 1990. If you ignore these differential operators that I wrote in here, and just plug in 0 here and 0 here, the integral from 0 to 0 from a to a is just going to be equal to 0. And now we just have this expression here. And I'm going to take the square root on both sides to get that f of 0 is equal to plus or minus the square root of 1990. Okay, plugging in f of 0 here, I'm just going to write it the equivalence relationship on this side. F of 0 is equal to e to the 0. E to the 0 is 1, so we get this is equal to our constant. Okay, so, I forgot to read off the question. This says find all functions mapping from the real numbers to the real numbers where f is continuously differentiable and it satisfies this equivalence relation. So I think based on the wording of the problem, we need functions. So this is kind of going to have to be written as a piecewise function, sort of. I'm just going to write it as two separate functions, call them f1 and f2. So I think it's going to be f1 of x is going to be the first one. I'll take the positive branch, positive square root 1990 times e to the x is going to be our first function that satisfies this relationship. And the second one, f2 of x equals negative square root of 1990 times e to the x. Sorry that square root was freaking ugly. But yeah, I think that's the right answer. I hope it is. It looks to be. And you can always just check. We can do a quick check. What's this derivative? This is going to be f1 prime of x is equal to e to the x times the square root of 1990. Yeah. So then we want to do this thing squared. It's going to be 1990 e to the 2x, and then we're going to have e to the t squared, so it's e to the 2t times 1990. And yeah, okay, so that should work out. I think that's the right answer. Sorry if that check was pretty sloppy. I just did it kind of fast in my head. But yeah, that I think that does it for problem B1. Hope this is the correct answer. It's not really a proof, but we can do a little circle QED. Yeah. All right. Goodbye.